Okay, question number 5. Show that the escape velocity is given by this, where g is the gravitational acceleration on the surface of a planet, and then r is the radius of the planet. Okay, so for this one, we are going to assume the planet to be the Earth. Okay, so let's try and do this. So we know that the escape velocity is derived by applying the conservation of energy. Okay, so this is basically the derivation. But let's try and do this together. So it apply the conservation of energy. Conservation of energy, which is delta K. Actually, this is total energy initial is equal to total energy final. So Ki plus Ui equal to Kf plus Uf. Okay, but we are gonna assume that we are gonna neglect air resistance and then assume the initial velocity is just large enough to allow the object to reach infinite with a speed of 0. So we are gonna let the velocity to equal to 0, hence we are gonna have final kinetic energy to be equal to 0, and then the potential energy final is also equal to 0 lah. Okay, so we are gonna only be left with 0 kan, so 0 0 and then 0. Okay, so we are gonna be left with Ki plus Ui equal to 0. Okay, so now we know that the initial apa tu nama dia, gravitational potential energy is equal to this. Okay, so we have K initial is half mv square, ini initial punya, and the gravitational potential energy initial is equal to gm mass of the earth over, I don't really remember actually, so mass of the earth r square, negative r square. Okay, so the escape velocity is the one yang initial ni is the escape velocity. Okay, so v half mvi square plus dengan negative g mass of the earth m over r square equal to 0. So we are gonna rearrange this. mv escape terus. I'm just gonna write escape velocity terus. So this is g mass of the earth m over r square. So the value of m here can be cancelled. The small m can be cancelled. So we are left with v escape square, I'm just gonna rearrange this, 2g mass of the earth over r square. Okay, and then we know that on the surface of the earth, g mass of earth is equal to g, which is equal to 9.81 lah. Okay, so we can then let this equal to 2gr 2gmer. We're gonna left with, wait, why am I confused? gr, oh okay, silap tertinggal. So we know this is gr. Okay, boleh yang ini ni dari formula ag equal to g mass of earth over r square. Kejap, I don't remember. I'm sorry. R square, yes, R square. So this is R square. So kita rearrange AG ni, kita let dia equal to GR square, GM, GR square. Janganlah shortcut, nanti tertinggal. So 2GM Earth is GR square over R. So ini boleh cancel satu. And then we are left with V escape 2GR. Okay, so this is shown. Itu kan soalan dia, show kan? Yeah. Okay, so that is how you derive the escape velocity. Lepas tu, we have to calculate the minimum speed required by a space shuttle to escape from a planet which has a mass half that of the Earth but equal in size. Okay, so now let's do that one. We are gonna use escape velocity equal to 2g mass of the Earth over, dia cakap dia same size kan, so radius dia akan sama lah dengan radius of the Earth. So this is like this. Okay, so this is 2, 6.67, 10, -11. Dia cakap tadi mass of the Earth, the mass of the planet is half of the mass of the Earth, so this is just half of the mass of the Earth lah. Okay, so half times 624 kilogram divide by the radius of the Earth, which is equal to 6.37. 6.37 berapa sudah? 6.37 mega. Okay, so 10 to the power of 6, square root this, and you should get the value, the escape velocity, to be equal to 7.94 times 10 to the power of 3 meter per second. Alright, so that is the solution for question number